Hi, my name is Mr. Evangelista, and welcome to another episode of Evangelista Science. We're going to be talking about 4-3 of the IB Chem SL curriculum, continuing on with covalent bonding. We're talking about this thing called VSEPR, or the valence shell electron pair repulsion. I know there's no T here, but this is valence shell electron pair repulsion theory. And to summarize this theory, it pretty much says that electrons are going to try to stay as far away from each other as possible. Right? So the trick on how to do these is first we gotta knock out some terminology. So we have these things called electron domains, and it's pretty much any place where we can find electrons. And we're gonna group those into two different groups. We're gonna call bonding domains and non-bonding domains. If we have any single, double, or triple bond, doesn't matter the type of bond. If it's a single bond, double bond, or a triple bond, it will count as a bonding domain. And if we have these kind of lone pairs, like these two X's here, or these X's here, those are called non-bonding domains. So let's take a look at this first one. Nitrogen is going to have 4 domains. 3 of them are going to be bonding domains, and 1 of them is going to be non-bonding. Carbon dioxide right here has 2 electron domains, and both of them are bonding domains. Again, it doesn't matter if it's a single bond, double bond, or triple bond. We're going to consider it as a bonding domain regardless. And for the third one, ozone, O3, we've got 2 bonding domains. Again, we do not discriminate between single bonds or double bonds, and 1 non-bonding domain. Okay? Now, what this allows us to do is once we have figured out the bonding and non-bonding domains, and we can use this chart to kind of figure out what is the shape of that molecule going to be. And so if we have, how to use this chart is the number of domains are listed here on the left. And so if we had 2 electron domains and 2 of them are bonding and 0 are non-bonding, then the shape is going to be linear. If we got 3 bonding domains, or 3 electron domains and 3 of them are bonding and 0 are non-bonding, then we're going to have planar triangular as the shape. If we're going to have 2 bonding domains and 1 non-bonding domain, then we're going to be V-shaped or bent. And that's how you use this chart. So let's go over some examples using some molecular models.
Okay, so let's actually take a look at some of these molecules. So the first one we're going to look at is this one. So we have 2 domains here, 2 electron domains, and both of them are going to be bonding domains. And so when we have this configuration, the angle between them is pretty simple, going to be 180 degrees. Doesn't matter if I look at it this way or this way or this way or flip it around this way. No matter how I turn it, it's going to be 180 degrees. This is also true of species with only 2 atoms in it. No matter how I do this around, it's going to be 180 degrees either way. So that is the linear conformation, pretty easy. The next one we're going to look at is right here. This is according to the IB, it's called triangular planar, or planar triangular. So the bond angle between these are going to be 120 degrees. And that's if you have 3 domains and all 3 are bonding electron domains. Now, as soon as we so let's just say that now we have 2 binding domains and 1 non-bonding domain. The angle is going to change a little bit. These electrons up here are going to push these kind of in a little bit. And so instead of being 120, the angle right here is going to be 117, so slightly less. We call this V-shaped or bent. Okay, V-shaped right here. V-shaped or bent. And the angle here is going to be 117. Okay, moving on to 4 binding domains. And if they were all bonding domains and 0 non-bonding domains, then we're going to get this shape, which is called tetrahedral. Now the angle in between each of these is going to be 109.5. 109.5 for tetrahedral. Okay. Let's remove 1 bonding domain, and so now we have 3 bonding domains and 1 non-bonding domain. Again, this is going to push this in a little bit, so instead of being 109.5, it's going to be 107. And this is now called pyramidal. It's kind of forms like a little pyramid shape there. And if we take off 1 more bonding domain, so now we have 2 bonding domains and 2 non-bonding domains, then the angle here is going to be 105. 105 now. This is the shape of water, and water having these electron domains here actually is a big reason why all of life is alive today. If this were not bent like this, then water would have very different properties than what we would see it have. And if it did not have these bonding domains, it would look like this, right? If it didn't have, it would be straight, it would be linear if it didn't have these two bonding domains. So thank goodness that these bonding domains exist, because it allows life to exist, all because water is bent like this and not bent like this. And we'll talk about that in the next section, talking about polarity.
Okay, one last thing we got to talk about is polarity. Now, we talked about a polar covalent bond, and a polar covalent bond is when we have unequal sharing of electrons. Now, what molecular polarity means that one part of the molecule is going to be positive and one part of the molecule is going to be negative. Now, this might seem confusing because a molecule that has polar bond might overall be a non-polar molecule, meaning it does not have a charge, even though the bonds inside of it are polar. Let's take a look at some examples. So your book gives these figures, which I thought were kind of hilarious, but also, surprisingly helpful at the same time. And so even though we've got polar bonds here, right? They're not really sharing equally. These gentlemen on the side are pulling more than the gentleman in the middle. But because of the symmetry, because there's symmetry in this molecule, their poles cancel each other out. Okay. Now this one, there's a little bit of fat shaming here. We've got a fat but stronger dude on this side and a not so fat, scrawnier guy on this side. And this bond is stronger than this bond, and so we have an overall polarity in this molecule. So this does not have symmetry, and therefore we do have a polar molecule here, okay? So skinny and fat people aside, let's take a look at some real molecules. So here's carbon dioxide. Oxygen is a lot more electronegative than carbon, so it's going to be pulling electrons this way. However, that is canceled out because of the symmetry of this molecule by this oxygen pulling carbon this way. So CO2, we are going to say, is a non-polar molecule. It is not polar. Same thing with BF3. Yes, these are polar bonds. However, the polar bonds have symmetry, and so therefore this molecule as a whole is non-polar. Same thing with this copper with 4 chlorines around it. Chlorine very electronegative compared to carbon, so we are going to have polar bonds here. However, the molecule as a whole, because of symmetry, does not have one side that is positive and one side that is negative. Let's take a look at this one. So carbon and hydrogen have very similar electronegativity. So this bond is not very polar. However, the carbon-chlorine bond is very polar, and so it's going to be pulling electrons towards this side. So this side of the molecule is actually going to be more negative, and this side of the molecule is going to be more positive. Take a look at NH3 or ammonia. Nitrogen, a lot more electronegative than hydrogen. It's going to be pulling electrons toward it, and so this side of the molecule is going to be negative, and the bottom side is going to be positive. Water. We talked about this, but the whole reason, a lot of the reasons water behaves the way it does is because of its shape. What it does is it allows it to have a negative charge over here on the oxygen and positive charges here on hydrogen. This allows for hydrogen bonding, which is, allows lakes to freeze from top to bottom, which keeps the fishes alive. And of course, anything that keeps fish alive and allows them to be caught by Mr. Evangelista is a good phenomenon.